Thank you so much for being here. So welcome to Rajat's PhD defense. Rajat is a PhD student in ICME, advised by Lexing and me jointly. And we have an interesting, fun story how we met. Before Rajat came to me to talk about the rotation in our group, I was actually aware of Rajat's blog, Identales. And that blog had amazing visualizations, especially there was one on neural tangent kernel. And that's the one I recommended to many other rotation students, probably including Rajat. Much later, I realized actually Rajat is the author of that blog. Right? I recommend you check it out. It's really cool. And what's really unique about him is he is passionate about understanding things very deeply and also communicate concepts very clearly, creating nice visualizations. And I've been so lucky that he joined my group and he inspired us with his way of thinking and thinking about the world visually. Although he worked on many different problems ranging from optimization to reinforcement learning to sketching, in the spirit of understanding things deeply, he today will focus on his latest work on co-designing randomized algorithms on modern compute systems.
Thank you so much, Mert, for the wonderful introduction. Yeah. And thanks everybody for being here. So yeah, welcome to my PhD defense. There's a lot going on for a title slide, but hopefully by the end, you guys will understand what's going on. Okay. So to get started, I'll just go at a high-level overview of all my PhD contributions. So over the years, as Mert said, I worked on a variety of topics and contributed to many different papers, and here's a list of them. So first, I'll just go at like a high-level overview of the papers, mainly on the left. And first, I'll talk about these three papers broadly under the umbrella of optimization. So the first one is on fixing the NTK. So Mert mentioned the blog post on the neural tangent kernel. So what this work does, it basically connects two theoretical analyses of deep learning. And one is the convex reformulation of neural network training, and another is the NTK. And it shows through the convex formulation that there are some limitations in the NTK viewpoint, which the convex formulation can fix. The next, I did this work with Lexing on showing that for finite horizon Markov decision processes, you can show that policy gradient methods can be cast as a linear programming optimization problem. And then finally, I also worked on this work on non-negative tensor trains, where sort of my main contribution was to extend constrained second-order optimization methods to tensor train models, and then use that to enforce positivity in their entries so that you could use it downstream for things like high-dimensional density estimation and variational inference. Then, so that was broadly more theoretical focused. And then through the PhD, I sort of wanted to do some more applied things. So the next couple of papers broadly also took a turn towards probabilistic methods and more so towards hardware-aware algorithms. So this work, which is sampling on metric graphs, I extended sampling algorithms to more continuous graph geometries. And then I think an important contribution in this work is that I also developed a fast, memory-efficient implementation of this new algorithm using CUDA, which is a programming language you use to program GPUs. Then in a similar vein, I also worked on MAT-RL, which introduces a reinforcement learning framework to understand, to automatically discover new algorithms for numerical linear algebra problems. And the important thing here is this framework is sort of tunes these discovered algorithms to both the input data and also characteristics of the target hardware on which you want to run them. And then sort of the culmination of my PhD is my most recent work, as Mert said, called FlashSketch. So this was just accepted to ICML as a spotlight paper. And at a high level, it deals with the problem of sparse sketching on modern computing hardware. So sparse sketches have been studied a lot theoretically, and they're very cheap in theory. But that doesn't translate naturally to actual performance on GPUs. And the reason for this is that the random sparsity that's introduced in them leads to irregular memory accesses. Now, the core contribution here is sort of to identify that this is a co-design problem, and then solve it by co-designing both a sketch and a kernel using hardware-informed structured randomness. And the headline result is that this achieves like a 1.7x geomean speedup over prior state of the art. So It's all right if you guys didn't understand all of that, right? Because the rest of the talk is going to be a deep dive into this paper. I'm going to build sort of all the context you need in terms of backgrounds on what sketching even is, how it's related to GPUs, so that what will follow naturally is the solution, which is FlashSketch. And then at the end, I'll conclude with empirical results and theory. Great. Okay, let's get started with the fun stuff. So first, some background on randomized numerical linear algebra. Now, I think at least probably half this room I have TA'd for 302. So we're going to look at ICME's favorite problem, AX equal B. Now, because I've TA'd all of you, I hope this needs no motivation. But nevertheless, I will list out a very small subset. You can use AX equal B. Your matrix A can be like conductance or stiffness matrices to solve network problems in engineering. They can be discretized PDE operators to solve a whole host of PDEs, very ICME. And something more, modern is set A to be the weights of a transformer and do things like model editing and logit inversion. So the way I like to think about AX equal B is you sort of visualize the matrices. Now, AX equal B comes in many shapes and sizes. The one we're interested in today is going to be this case where A is a tall matrix. And most of the stuff I say will apply to the other sides too, but it's easier to think about it this way. And some notation, A is going to have D columns and N rows. Now, we know that this is an overdetermined system of linear equations. So the first thing you do in 302 is, well, how do you solve this? You do least squares, right? And then the computational complexity of solving this using least squares, usually no matter what technique you use, is going to be n times t squared. So this is all just numerical linear algebra. What randomized numerical linear algebra tries to do is, well, can we reduce how much work we have to do to solve this least squares problem? And it does this using a very simple idea, which is, okay, what if I just multiply by a fat matrix S, okay? Where S has m rows and n columns to sort of try to reduce the problem size. And the key point here is S is a random matrix. Okay, what this means is every entry in S is an IID random Gaussian variable, and you sort of normalize it so that the norms stay same. Then the idea is you do this matrix multiplication and you get a smaller least squares problem, right? And the point is you work in regimes where this computational complexity, which is first doing the matmul and then doing a smaller least squares, should be lesser than solving the full least squares. But you should immediately ask, well, those two things are actually different problems, right? Like I just multiplied by a random matrix. Right? This is like, okay, we're not solving the same thing anymore. So there's no reason this should work, right? Well, we could see what happens. You could just do it, right? So let's take some transformer weights and try to do least squares with sketching. So I plot here like the error, relative error between the classical least squares and the sketch least squares, and I vary the sketch dimension n. And we see a very nice trend where it gets better and better, closer to machine precision. Now, of course, the point here is, okay, this should be faster than that, right? And in this regime with these sizes, you can measure the wall clock time, and it's also true in terms of wall clock time. So this is pretty good. Randomized numerical linear algebra works. And I just did least squares, but there's a whole host of other things you do in 302, which is all of classical NLA. You can do a RAND NLA version of this by just sketching first. Okay, so the summary of RAND NLA is just do numerical linear algebra on S times A instead of A. Okay, but the question still remains, why does this even work, right? Why does RAND NLA work? And this goes back to a very beautiful mathematical result, actually from the 1980s, called the Johnson-Lindenstrauss lemma. Now, I first learned this lemma in CME 309, which was taught by none other than Mary Wooters, who's in my chair. So the JL lemma comes in, there are many different flavors of the JL lemma. The one we're going to be focusing on today is the one for subspaces, okay? So let's go back to our least squares problem, right? So what does the least squares problem do? You want to project B onto the column space of A. So to better think about the column space of A, let's take a QR factorization of A, right? So now we have a matrix U, which is basically an orthonormal basis for the column space of A. Now, how do you think about the column space of A? Well, first, let's start with the vector X in RD. Okay, so 1 point X in RD. And if I multiply by A, or if I multiply by U, RD is going to be mapped to a subspace, which is a D-dimensional subspace in Rn. Okay, for simplicity, I'm going to treat A as a full rank matrix. Okay, so we have now a subspace which is d-dimensional embedded in an ambient dimension Rn. Okay, and now what happens when we apply the sketch is this goes back down to an m-dimensional space. Okay, now what the Johnson-Lindenstrauss lemma says intuitively is that if S is that random matrix that we chose earlier with IID normal entries, that random projection approximately preserves the geometry in this subspace. Okay, that's the high-level vibes. But the JL lemma does more. It precisely quantifies this. What does it mean to approximately preserve subspace geometry? Well, you can define a notion of distortion, a quantity epsilon, which basically says, okay, let me look at the norms of vectors in RD, get them through this whole process and see what happens to their norms. And epsilon is basically a notion of relative error in your norm. So it's a multiplicative error in how much my norms distort within my subspace. And the JL lemma says, well, okay, if you have a distortion of epsilon, if you want a distortion of epsilon, the sketch dimension should scale as d over epsilon squared. I'm like ignoring constants here. Okay, and so this is one way you can define epsilon. You can also define epsilon in terms of how close to an orthonormal matrix S times U is. Okay, now this is a really beautiful result. And then I get one thing I really want to highlight here is in this expression, n doesn't even show up. Okay, it doesn't matter what dimension your subspace is embedded in. If you want distortion epsilon, you just need 1 over epsilon squared, right? Or d over epsilon squared. Right? So the n doesn't even matter here, which is actually a very non-intuitive thing for me. But yeah, so this is sort of an explanation of why multiplying by a random matrix even makes sense. And the nice thing is you can also see this in practice very easily. So for that, I like to sort of reframe this expression here to think about how does my distortion scale with my sketch dimension m. Okay, so epsilon goes is 1 over square root of m, and you can just do this. You can like take a matrix, look at its column space, multiply by random matrices, sketch it, compute distortions. There's a few lines of NumPy, and plot it. And you get this very beautiful curve, which is minus 0.5, which matches with the theory exactly. Okay, great. Now, the other thing, right, is I think this is a thing which a bunch of us ICME folk would love, is that basically we know that matrices and graphs are kind of the same thing, right? So when we look at this matrix multiplication, S times A, we can instead look at it from a graph point, where we assign a node to each row of A and a node to each row of Y. And then we assign weights to the bipartite graph over here based on the values in S. So a row of S would correspond to all the edges from the rows of A to one output row in Y. And a column of S would correspond to all the edges from one row of A to all the rows in Y, right? So the full matrix S implies a bunch of weights on this bipartite graph, right? And sort of the intuition here is you can think of each output coordinate in your sketched space to be sort of a random mixing of all your input coordinates. Now, the nice thing about introducing this graph picture is you can think of the problem of, okay, what if I want to design other sketches? You could reframe it as, okay, now it's sort of like, how can I sample other graphs, right? And there's a whole host of theoretical work on this, which is how can I sample a random bipartite graph to have certain properties for sketching? And this relates to things like expander graphs and a whole host of other things, a whole can of worms. But and then the other thing over here is I've highlighted the word all here, right? So that means every input coordinate is being mixed into every output coordinate. So what does that mean? That means S is a full dense matrix. Now, a natural idea, which is to sort of say, okay, if I want to make applying sketches faster, is I could do sparse sketching. So what does this mean? Well, okay, I look at the sketch matrix S, and I could just say, well, what if I just set some of these entries to be 0, right? And specifically, I choose them to be random. The locations of my sketching matrix, which are non-zero, I'm going to choose those to be random. And this is a sketch that has been very well studied. It's a sketch called the Sparse Johnson-Lindenstrauss transform. Okay, so I did one extra little thing here. We went from Gaussian random variables to just plus minus 1 uniform random variables. Now, the main sort of recent theoretical results, this sketch has been very well studied, it's also called the SJLT for short, is that you basically get the same guarantees as the normal JL lemma for a dense sketching matrix, but it's not fully free. You can't just sparsify a matrix S and get exactly the same results. There's one extra condition, which is a condition on the column sparsity of S, right? So what we said was, okay, we're going to choose non-zero locations in my S, but I need to have some, at least 1/epsilon of them per column to be non-zero. Now, intuitively, you can go back to the graph picture and say that what this is saying is each input coordinate is mixed into at least 1/epsilon output coordinates, right? And in terms of the graph, what this means is this is basically a statement about the left degree of this bipartite graph, okay? So every single row here has at least S output rows. And to make it nice and structured, we'll just say all input rows are mapped to exactly S output rows. Cool. Now, again, the same sort of theoretical stuff. You can do a lot more smart things about how you sample these sparse sketches, but I want to take a slightly different turn and not focus on purely on the theory, but talk about how we actually compute these sparse sketches in practice, right? That was the whole motivation of designing sparse sketches is, well, if you wanted to do dense S times A, that would be M times N times D flops. But if you want to do sparse S times A, that would be S times N times D flops. Why? Because if a lot of my entries are 0, I don't need to do 0 times something to know that it's 0, right? So in my computer, I can skip those computations and do lesser flops, right? And of course, we're going to sort of operate in the regime where, okay, our sketch dimension is very big, and we have a very few number of non-zeros per column, right? So sparse must be faster, right? But if you're a numerical linear algebra enjoyer in 2026, you're going to be doing these things on GPUs, okay? And it's not so clear now that sparse must be faster, okay? So I'm going to do a very simple experiment, okay? So if I want to do a sparse matmul on GPUs, I'm going to use the thing NVIDIA gives me, which is cuSparse, okay? cuSparse is a software library to do fast matrix multiplications on GPUs for sparse matrices, okay? Specifically, it's a library that doesn't do the redundant computation on zeros, okay? It's like aware of your sparse structure, so it tries to save on computational work. The experiment over here is I'm just going to vary the density of non-zeros in my matrices, and I'm just going to fix the sizes, okay? And we're going to measure how long a matrix multiplication on a GPU takes using cuSparse. And it's pretty reasonable to expect, as we increase the number of non-zeros, the time it takes to do this matmul increases because we're doing more flops, right? And this library is pretty smart. It's not going to do the redundant computation on all the zeros in the top. Okay, seems pretty good, right? We're computing sparse guesses on GPUs. But I'm going to do another experiment, which is kind of a bit silly, which is, okay, so cuSparse is like, I know exactly where the non-zeros are. I'm going to skip all the zeros. There's another alternative, which is, okay, you give me a sparse matrix. I don't really care. I'm just going to fully densify it, okay? I'm going to fully densify it with all the zeros, okay? Big matrix with a bunch of zeros and many non-zeros. And I'm just going to do dense matrix multiplication. Again, I'm going to do this using the stuff NVIDIA gives, which is cuBLAS. cuBLAS is their software library to do super fast matrix multiplications on GPUs, okay? Heavily optimized. Now, remember, this is quite a dense thing to do, right? Because all I'm doing is doing a lot of 0 times x plus 0, right? So this sort of axis doesn't really matter for this column, right? Whatever the values are, cuBLAS doesn't care. It's still just going to do the computing. So all the times here should be the same. And when you measure it, it is true, right? Roughly the same. It's also within the measurement noise of this experiment. But if you look at these times closely, there's a pretty big problem, right? Which is, if your density is like more than 5%, cuBLAS is actually faster than cuSparse. Now, to be clear, this column is necessarily just doing fewer flops than this column, right? And this column is like very fast compared to this column as the density goes up, right? So what this says is that sparse is not automatically faster. Now, the thing about GPUs, which a lot of you might know, is that, okay, they're all about like parallel computing, right? But I want to stress this is not just about parallelism, because whatever because both of these computations are the same matrix multiplication. So it's not like Sparse is like somehow being less parallel than cuBLAS, right? These are like NVIDIA libraries running on GPUs, doing the exact same compute, leveraging the exact same amount of parallelism. Right? So there is something more. So simply having better computational complexity in terms of flops does not necessarily mean it's going to run faster. So let's try to understand at an abstract level why. So the main thing here is what we're missing is the fact that, okay, our input lives in some part of our computer, and that lives far away from where the actual compute happens in the computer. So if you want to perform an algorithm, you got to move your input to the compute area, do the compute, and then move it back to the output area, right? And this data movement takes time, right? And the amount of stuff that the compute can hold is small compared to your whole input. So you can't just be like, oh, I'll move all my input, do all my compute, and move it all out to the output. And this is sort of a fundamental sort of property of how these GPUs are constructed. And when you talk about computational complexity, all you're talking about is how much work you're doing here. You don't really talk about how much work it is to move stuff, right? And so what is the difference between cuSparse and cuBLAS? Even though they're doing the same effective compute, the way they move data is different, right? cuSparse is sort of trying to be smart. It knows where the non-zeros are, but that means it's going to be more inefficient in terms of how much data it's moving. cuBLAS has been optimized to be like, okay, all my data is very nice and structured. It's a big tile, I can move it faster, right? And right now, none of this is like special to GPUs, but why wouldn't something like this happen in CPU as well? Because the hardware also has properties, which is how many flops can it do and how much data can it move, right? So now the trade-off that you have to balance is not only properties about the algorithm, but how the GPU, how your hardware is good at doing both these things. So your algorithm implementation has some characteristics in terms of how much data it moves and how much compute it does. And your device has a capability, how much data can it move per second and how much compute can it do per second. And basically in the low sparsity regime, cuSparse is much more optimized and tuned to the capability of the GPU. But that is no longer true when the sparsity becomes high. Okay, so this is like a pretty like abstract sort of representation of what a GPU is, right? So, and a lot of people talk a lot about GPUs and stuff, but let's actually look at how a real GPU looks, right, in all its glory. So this is an RTX 4090. Now, if you ask me, this is truly an engineering marvel, you know. I would go far as to say, honestly, a modern wonder of the world. The chip over there has like 76 billion transistors, right? And they're all like sort of assembled to do this compute. They're sort of like cathedrals etched in silicon. Now, the part that we're going to be interested in, right, is just the central area. Okay. Now you'll notice there are these squares around the central chip. These squares are the global memory. Okay. So this is where the input and output live. Okay. So remember in our abstract picture, we had these input and output. Where do they actually live? In these chips. Okay. They're also go by like VRAM, right? And the 4090 over here can hold like 24 gigabytes of stuff. Now for our level of abstraction, we're just going to say, okay, this whole global memory is just this big grid of cells, okay? And like each little cell can hold a number. And the big, crazy chip over here, we're going to just simplify that into this toy GPU model that we're going to be looking at, okay? So I'll go through each of the parts over here and explain what this model is. So first, we have these wires, which is like the global memory bus, and this is basically the wires through which data moves from the global memory into the main stuff in the chip. Now, what's the main stuff in the chip? It's organized into a bunch of these units called streaming multiprocessors. Now, what you should think about is each streaming multiprocessor is a little mini full-blown computer with a lot of like parallel compute capability, right? Now, I'm showing two of them. The actual 4090 has 128 of them. Now, within the streaming multiprocessor, we also have some more memory, okay? This memory is called the shared memory. It's kind of shared. It's also called the L1 cache. And fundamentally, it's sort of different from the global memory in the sense that it's much faster to read and write from it, but it's much smaller. And there is yet another tier of memory called the register memory, right? This is now again sort of going up the hierarchy where it's even smaller than the shared memory. There's very, very few registers in an SM compared to the shared memory, but it's much, much faster. Now, what you should think about this is when I move those squares from the input to the compute blob, you should think about the registers as being the place where the squares live in the compute blob, because the actual compute units in your SM operate on these registers, right? So these are the parts of the circuit that does the math, that does the arithmetic. Okay. Now, the other property of these SMs is they are massively parallel. What that means is there are many threads of execution that can happen in parallel. And for our purposes, we're just going to abstract that away as like, okay, I'm just going to show like a little dot to show what this thread is doing. It's sort of like a status indicator. And each thread owns this little slice of registers. Okay. So now when you want to program your GPU, what you're going to be doing is you're going to be writing a program that every single thread runs, right? One single program that all the threads run. Okay, so that's how you sort of instruct what your GPU is going to be doing. And the sort of language you write that program in is called CUDA, and that little program is called a CUDA kernel, right? Just to get some terminology out of it. So now if we go back to that input, compute, output cycle, how would that look on this GPU? Well, first, you're going to move stuff from global memory to shared memory, right? Then you'll move it from shared memory to registers. And then once you have your input data in the registers, you can actually do the compute, and the output of the compute still lives in your registers. So now you have to write it out back into the shared memory, and then from the shared memory to the global memory, right? So the main sort of takeaway that I want you guys to have from like our abstract blobs is that it's sort of very similar to that, but now there's a hierarchy of memory, right? It's like, okay, I can move data into an intermediate space that's slightly bit smaller but faster to access. Then there's another hierarchy where before I can get to the compute. So what this hierarchy sort of implies is that, well, if I want to sort of optimize my data movement and compute balance, I should also take into account whether I could use this hierarchy effectively, right? So just as an example, like what does that mean, right? Well, I'm going to show you a kernel for doing just standard matrix multiplication. Okay, so we're going to look at A times B to give C. Okay, and so these two SMs are only going to sort of be responsible for these sub blocks of A times B equals C. Okay, and I'm going to let the whole sort of parallel animation just run through, and like the details of the matrix multiplication algorithm don't matter too much. What I want you guys to focus on is basically try to see that, okay, once I move data from the global memory to the shared memory, I want to sort of reuse it as much as I can once it's in the shared memory before I write it back out, because moving data takes time and I want to be efficient with it, right? So if you let this whole algorithm run, you can see, okay, I'm going to like sort of load stuff from the global memory to the shared memory. And then once it gets into the registers, the compute start computing away, right? But if you sort of like focus your attention on one SM, you can see that there's a lot of reuse going on. And the reason this reuse is possible is because you're doing local computation. Okay, so it's a property of what matrix multiplication is, that once you bring a tile into shared memory, you can do a lot of repeated compute with the same data, right? So, and that's really good for GPUs is if you have localized computation. Okay, great. So we talked a bunch about sparse sketching, then talked a bunch about GPUs. Before we get to sort of the main idea of FlashSketch, I do want to talk about, well, one way to do sparse JL on GPUs is to just use sparse, right? But you could also talk about, but there has been work on trying to write a specialized CUDA kernel for implementing sparse JL on GPUs, right? So and it will be very instructive to go over one of these existing algorithms, because the inspiration for FlashSketch comes from looking at what can be improved in this algorithm. So one simple idea is, okay, if I look at my sketch operation, right, and I look at the outer product form of this matrix multiplication, right, S is on the left. What that means is one row of A corresponds to contributes to 2 rows of Y, right? So a simple idea is, okay, I'll just say this row is like one thread's responsibility, okay? And it's going to do these 2 contributions sequentially. So what that means is it's going to load the entry of A, load the entry of S and Y, do the math, and accumulate back. Okay. Once it does that, then it can move on to the next contribution. And this is nice because even though this is sequential, S is pretty small, so it's not going to be a lot of sequential work, right? And then you say, oh, I'll just let all my threads do this in parallel. The problem is it doesn't exactly work because, well, what if two threads are trying to contribute to the same row, right, of Y, and they both read an entry of Y, and then they do their compute, and now like, okay, which value goes here, right? Like both of these are like, you can't really add them together. You can't write one of them because it's sort of an in-between answer. What you need to do instead is you need to serialize them. And the way you do this is using something called an atomic update. Now, what an atomic update does is it first loads, it sort of says, okay, if two threads want to work on one thing, you sort of force them to go in a line. Okay. So that means, okay, this thread does its compute first. And once it's done, the next thread can take its turn and do its version of the addition. Okay, so this is sort of like the description of this algorithm in this picture. We could also see how it looks on our GPU model. Okay, and the way I'm going to represent this is if one thread is sort of waiting for another thread to do its atomic operation, it's sort of locked on one location, right? So that might have been a little fast. So let's sort of pause at one of them and let's look at what's happening, right? So this thread is like, okay, I'm doing my atomic operation on this memory. So it's holding a lock on that global memory location. And this thread also wants to do its atomic operation, but it needs to wait for this lock to be released. So right now, this thread is basically just doing nothing. It's just waiting. Now, what needs to happen is, okay, this thread needs to read all the way from global memory to shared into the register, do its compute, its modify operation, and then write back. Now, throughout this whole cycle, this thread is just waiting, right? And then once this write back is done, the lock is released, and this thread can take its turn to do its update. Right? It's the same cycle. And I want to sort of stress that kind of slow because it's doing a full round trip from global memory to shared memory for every single update, right? And we can sort of let the rest of the algorithm run. I don't want to do the whole thing because that will take a while. But the reason for this happening is that fundamentally this computation is quite non-local, right? Like whatever the reason you had to use this atomic in the first place was you couldn't sort of get all of these entries within one SM, work on it, and then write it out. It's across SMs, right? And if you sort of, at this point, right, I sort of built up all of this context, right? And like to sort of summarize it into what we've observed is like, okay, why is this non-local in the first place, right? It's non-local because these non-zero locations are like random, right? And why are they random? Well, we chose them to be random so that our sketch could be good, right? But the very thing that makes the sketch good sort of hurts what the GPU wants. The GPU wants computation to be local, right? This is sort of like a math versus machine scenario, right? So once I sort of accumulated all of this understanding, the natural thing which I decided, which I sort of thought of was, okay, the one thing like you could try and be like, okay, maybe we could write a smarter CUDA kernel, something better to sort of implement the SGLT faster, right? But the goal here is not to implement the SGLT faster. The goal here is to sketch faster, right? Which means changing the sketch is fair game, right? So if you want to sort of balance the tension between math and machine, you sort of put both of them in a room together and negotiate. Okay, so let's see what that means. So let's balance this tension. Okay, so yeah, the issue here was non-local computation, right? One row of Y is getting input from all over A, right? More specifically, what this means is there are cross-SM global atomics, right? And if it's cross-SM, you must sort of do a full round trip through global memory, which takes a lot of time. Well, if the sketch is fair game, why don't I just change the sketch to localize the computation? Okay. precisely what I mean is, what if you make the sketch a block diagonal sketch, and you sort of choose each block to be an SJLT, and you choose the block size such that all the rows corresponding to one output row can sort of fit within one SM. And then you don't need to load Y sequentially. You could load it once into shared memory and do shared memory atomics instead of global memory atomics, right? And those would be much faster because writing and reading from shared memory is much faster. Now, this is great because if you make your sketch block diagonal, this applies for all rows of Y, right? And you have like fully, eliminated the global atomic problem. But the problem with this localized computation is you're in this room negotiating with math and machine, and then now like math is a bit sad because let's try to look at what the sketch is actually doing, right? If the sketch is a block diagonal sketch, well, that's just saying I'm just going to like chunk up A into blocks and then independently sketch them, right? And what does this mean? That means I'm just going to be doing a smaller sketch, right? Because this is a smaller sketch. And go back to the jail lemma in the start, the quality of the sketch depends on the output dimension. Sure, n is smaller, but n doesn't matter, right? So if you look at one input block of A, it goes to one output block of Y. And the other thing I want to stress is, okay, what decides the block size, right? Because the block size is what decides what the sketch dimension is, and that's too small, we're saying. Well, what decides the block size is what can fit in one SM, right? One SM of shared memory, one SM's shared memory, and how many threads it can support. And what decides that? Well, the laws of physics decide that, right? And like, if we're trying to decide a sketch, we don't want to be sort of bound to like what the GPUs are saying, right? If you're saying, oh, I can only sketch up to 128 dimensions, that's not going to work for large scale sketching. Great. So what the problem basically is that the randomness in our sketch is now a bit too constrained. But this observation that these sort of sketches are fully independent, another way to say the same thing is, well, I could have the sketch be a block permutation, right? And this is basically exactly the same thing. It doesn't matter how I arrange my output blocks, right? I'm just doing 5 independent sketches and then sticking them together. What order I stick them together in doesn't really matter. So, okay, that's an interesting observation. And now the problem is, okay, how do we add back randomness to the sketch, right? Well, we see all these permutations are kind of the same. What if we just did 2 permutations and then unioned them? Okay, and more specifically, you choose these permutations to be random, right? So what we have now, the sketch is sort of a block permutation, and where each block is an SJLT, right? So in my very creative I made a very creative decision to call it block perm SJLT, right? Now, let's sort of define some things here. The number of permutations is kappa, and the sparsity within each block is S. Okay? And one important thing over here is you sort of choose these permutations to be edge disjunct. What this means is you don't have a block that collides with each permutation. So what that means is every block row and block column of S has the same number of non-zero blocks. So let's look at properties of this sketch. Well, this is pretty good from a computation point of view, right? It's like somewhat local because you have contributions from 2 blocks, and within each block, it's local. The randomness is also, math is also pretty happy because, well, it's not like you're just doing 5 independent SJLTs. There is mixing across the different SJLTs, right? And the other nice thing about the sketch is you could tune it, right? Maybe it so happens that this single permutation is actually good enough for your actual sketch. Maybe you need a lot of permutations, right? This kappa is actually just a trade-off between how good your sketch is and how local your computation is, right? And the point here is we introduced structure in the randomness of S, and the structure was informed by properties of the hardware on which we want to run the sketch, right? So FlashSketch is basically the actual CUDA implementation of the sketch with like the whole shared memory atomics and stuff. And I'm just going to show how it looks in our GPU. There's one additional detail, which is, okay, the actual sketching matrix we don't actually need to store. This is another optimization which we did, which is you don't have to actually store S in your global memory. You can generate it on the fly. Because if I'm like a sketch consumer, I kind of don't need to know exactly what sketching matrix you used. It's like, I'll give you A, sketch it for me, and give me Y, right? So this saves some more on data movement, right? Again, I'm only going to show a portion of the sketch, and I'm just going to let the animation run, and sort of we can see now the atomic locks are no longer to global memory, but they're all within shared memory. Specifically, they're all within one SM, right? And we can go through sort of the same sequence, right? Where one thread is holding a shared memory lock and the other one is waiting on the shared memory atomic. And then if you do your read, modify, and write cycle, it's much faster because you're not doing a full global memory round trip. So you're being much more efficient in terms of data movement. Okay, that was great. So now we sort of understand what the sketch is, but the question is still like, okay, does this actually work, right? We sort of made this toy GPU model and we had some intuitions and that informed what we should do. So now let's actually look at the results. Now, what do you care about when you're doing sketch? There's two things, right? One is the speed, how fast you apply the sketch. The next thing is how good the sketch is. Well, that depends on what you're actually going to do with the sketch. In RAND NLA, the metrics are things like distortion, right? Which is what we saw earlier, but it could also just be error with the eventual target from the classical method. Now, you could also use sketching in a lot of machine learning pipelines, and they have their own whole host of metrics, right? And I'll show one example at the end of the results section. So let's just start off with an example from RAND NLA, which is just gram matrix approximation. So this is very similar to the epsilon metric we showed in terms of the subspace approximation, but it's basically you're trying to approximate A transpose A with SA transpose SA. Okay. And what we're going to plot is the quality metric we're interested in on the y-axis and the actual time it takes to apply the sketch on the x-axis, right? So this is a speed quality Pareto curve. And what we want is we want faster and better quality, so we want to be close to the origin. Great. So, and remember, this is just any sketch. It's not like only sparse sketches or dense sketches. So one sort of, and what I'm going to vary in this plot is the sketch dimension. So I'm going to fix the input size and vary the sketch dimension. So if you plot, let's say, the classical dense Gaussian, right, and you use cuBLAS to do this dense matmul, this is how the curve is going to look. Now, a bunch of baselines to implement the SJLT. There are two different implementations. One is using cuSparse, and this kernel is the global atomic kernel I mentioned earlier. And then the subsampled fast Hadamard transform is another baseline that I won't get into in detail. Now, if you look at how FlashSketch looks, it's getting the same sketch quality, but is much faster, right? So it's pushing the Pareto frontier. We can see how this looks for sketch and ridge regression. It's the same thing. You get basically the same quality end-to-end for much faster sketch time. And very briefly, I want to talk about an end-to-end machine learning task called data attribution. So this is from the same work that introduced the custom kernel for the SJLT. What data attribution is at a high level is, okay, you have some machine learning model that's been trained on data. You compute gradients for your whole training set. And then you get a new point and you want to sort of attribute what part of your data set influences your prediction on that. The way you do that is you do affinity with your gradients. And what this paper introduced was, well, to make this more scalable, you can compress your gradients using sketching, right? And then the metric you care about in data attribution is something called the linear data modeling score. I won't get into the details of it, but the summary is you want this to be higher, right? And you can make sort of a similar Pareto plot. This time you want to be in the top left corner. And again, FlashSketch is pushing the Pareto frontier. And then a final sort of result I want to show is we mentioned that we can sort of use kappa to tune this trade-off between how fast our sketch is and how good our sketch is, right? And you can actually see that in this synthetic example, right? You increase your kappa, your error improves, but the sketching time increases. Great. So I just showed you like plots on specific sizes, but of course we ran benchmarks on a bunch of different sizes, bunch of different problems, and then the geometric mean speed up is around 1.7. and you maintain the same sketch quality. And this is a speed up over the next best baseline, right? So basically, the summary from this result section is if you want to sketch, use FlashSketch. Okay, so that's the results from the machine point of view. There are results from the math point of view as well. So very briefly, I would like to conclude with a summary of the theory. Again, we're going to be looking at U instead of A, which is an orthonormal basis for the column space of A. And to sort of understand the theoretical properties of the sketch, we're going to define a quantity called the neighborhood coherence. So some notation here, we're going to define the permutations by pi. The number of blocks you have is capital M. And for each sort of index, I'm going to define a neighborhood. So then the neighborhood is basically, if you look at the first block row, the neighborhood of the first row is the non-zero permutations in this row. So for this example, it's 1 and 3, right? Now for each neighborhood, you sort of look at the corresponding blocks of U, and then you stack them together, right? And then you take their norms, and the max of that norm gives you the neighborhood coherence. Sort of to work through the example in this case is, okay, this block row will give you this neighborhood block. And you basically do this for all 5 block rows, computing the neighborhood energies in each case. So the sort of the intuition here is you should think of these neighborhoods as sort of sets of coordinates, and this energy being like how much of my column space, the subspace, is contained in these neighborhood coordinates, right? And then this max is basically saying which neighborhood has the most amount of, does my subspace have the most amount of energy in, right? And I'm just going to define a couple of other things. One is the block coherence, which is basically the neighborhood coherence with one permutation. So it's basically saying which block of U has the most subspace energy. And then these things are sort of scaled so that, so first of all, the neighborhood coherence is always less than or equal to the block. And they're scaled so that the block coherence is between 1 and M, and the neighborhood coherence is between 1 and M over capital. So this is just to get a feel for what these quantities look like. So our main theoretical result is basically the same sort of distortion guarantee as the GL lemma. And we have the following scaling for the sketch dimension. So this is the full final sketch dimension, right? You get the same 1 over epsilon squared scaling, but now you have a factor which is a neighborhood coherence which controls this. Now in this, I'm ignoring like log factors and constants. And you have the same sort of threshold on the sparsity. Remember, kappa times S is the net column sparsity. Now, one catch here is this theorem was with fixed permutations, but the whole point is to randomize the permutations. And we can also show that if you randomize your permutations, you can control the neighborhood coherence, right? So specifically, if you choose your permutations to be independent, uniform, random, you can show that the neighborhood coherence is sort of not too far away from 1, and the deviation from 1 goes down as you increase kappa. Now, I've talked a lot about sketching, so what better way than to end with a proof sketch? So this is going to be very quick. So the neighborhood energies that we talked about were like a sum of block energies, right? And if you choose the permutations to be random, they're going to be random blocks. And then you can show that the mean block energy is 1. So, okay, you have sum of random variables with mean 1. The variables are matrices, so you can just use matrix Chernoff to control the deviation from them. Great. So now I'd just like to close with a summary. So in summary, we saw that, okay, sparse sketches were pretty mathematically efficient, but not the best for GPUs. So then we saw the main insight was, okay, we can sort of, both parts are fair game, so we can design them together. FlashSketch does that and pushes the Pareto frontier. Now, this is sort of a broader lesson that I'd like to sort of emphasize, that FlashSketch is just one instance of where if you want to do effective algorithm design with modern systems, you've got to sort of reconcile both the math and the theory with the reality of what you're doing your algorithm on, what compute you're doing. So that sort of concludes the technical portion of this talk. And now, very briefly, before I'll just spend the last few minutes on like acknowledgements. And before I get to acknowledgements, I also have a little bonus slide. All these animations were made using a Python library called Manim by 3Blue1Brown. And then I feel like some of you in this room might be a little concerned that I somehow managed to talk for 1 hour without bringing up AI, but worry not, because a lot of tokens were used in making all of these Python animations.